So, as I mentioned, since the recording has started, I want to mention again that the quiz will cover the homework 1 and 2 and homework 3. Up until today, what we learn, it will be in the quiz, and the chapter 1 and chapter 2 will be completely covered by in the test 1, which will be the following week. So let me share with you the date. Exact date will be 19th, June the 19th. It will remain open from 6 p.m. till 10 p.m. on Wednesday, so that people who work in the morning, they can still have some time to take the test. And the test will be about 75 minutes, 70 to 75 minutes long. And all the test or quizzes, they are MCQs type, and you will be immediately given the score, but you are still required to upload your work on the assignment Dropbox. If you have any concern, you can ask your professor. I'm muting my mic. Okay, let us begin our lecture now. So we studied about up until here. So let me open my notes here. These are the objectives of this chapter. And at the end of the chapter, you should be able to learn about types of energies, mass flow rate, heat transfer. So our main focus will be types of energies and heat transfer. So let me share with you just a big picture. For example, energies. So usually we take small energies. Like small letters for energy means specific energy. I'm sorry, this is like, and when you specify something, you are dividing it by certain quantity such as mass in this case. And just another thing you will study here is m dot. Dot stands for flow rate. That what is the mass flow rate? And there are different formulae, like if you have a container, this is just a big picture, okay? I'm not going into the detail right now. So you open the tap water, and the tap water starts, the level goes up, up, up. So like if I say mass flow rate, or you can say this is also like rho. If I say mass flow rate, the unit is kilograms per second. And do you remember the density? The density formula is mass per unit volume. You guys have understood this, but it can also be written like mass flow rate per volume flow rate, and volume flow rate is in volume per unit time. And this can also be written as the area times the velocity, because suppose if you have a pipe, it's a cross section. So it has a cross section A. And if I have the velocity of a fluid passing through the pipeline, average velocity, so volume flow rate would be small v, which is showing the velocity, small v, not the volume, but the velocity times the area. It is telling you the volume flow rate. So if I write down the mass flow rate in terms of density from here, can I write down like this? Yes, I can. Look, density is the unit of density is kilogram per meter cubed, and the unit of volume flow rate is meter cubed per second. And finally, you will get your unit kilogram per second. This is how you will be having the consistency in the units. So this is a big picture which I'm telling you. And why are we so concerned about finding the mass flow rate? I'm telling you why, because sometimes we need to find out the power. Suppose power of a device. I'll let you know what is power of the device in a bit, but let me show you. It is usually written by E dot. Like E dot is mass flow rate, the same E which you wrote down over here, or you will multiply by E. And now to find out the unit of power, we know the mass flow rate has a unit kilogram per second times the unit of E, which is kilojoules per kilogram. And if you do the simplification, you are left with kilojoules per second or kilowatts, because we know that 1 joule per second equals to 1 watt. So this is again the big picture where we are heading to. For example, if you have a nozzle, okay, just a big picture, and over here the water is flowing. Initially it is suppose the water over here is suppose it is very small, like suppose this is 0 meters. It may not be zero, but let's say it is, for instance, if it is zero, for example, it doesn't make sense, but assuming this, and the velocity v2 is 10 meters per second after it passes through the nozzle. So if I say, what is the power generated by this nozzle? So you will start your problem by this formula. And in order to find out the mass flow rate, and first of all, you find out the specific energy, half v square. Why am I not writing mass? Because this is a specific energy divided by mass. Velocity, velocity. Okay, guys. So if you're confused that why have I not chosen, so let me show you. This would be like 100 divided by 250. But if you, this is joules per kilogram. But if you are concerned about, professor, why haven't you selected velocity here? So let's say if it is 2 meters per second, so you can still use the difference of 2 points, energy in 2 points, half v2 square minus v1 square. this will give you the this will give you the energy generated by the nozzle, and half 10 square minus 2 square. Okay, guys, now in order to get this answer, so let's find out. So one more thing I want to mention here, this is in joules per kilogram. And now if I write down, if I multiply, what is mass flow rate? Mass flow rate, if it is water, so you can say mass flow rate of water. The density of water is 1000. Generally speaking, it is 1000 kilogram per meter cubed. Okay, guys, so this is 1000 kilogram per meter cubed. Okay, guys, now in order to find the mass flow rate, we should know what is the volume flow rate. And volume flow rate is area times the velocity. So now this is a little bit lengthy problem, but I'm just explaining that how would you solve. Suppose we average is 5, area is average. So we will go over it later on. I was making up my own problem, but this is how we are going to see the problems in this chapter. Another thing which I'm going to show you in this chapter, which may not be starting today because this is another main objective, is about the heat transfer. This is the type of how would you transfer the heat from one body to another body. So so we will study about the, for example, if you have a wall and you are sitting inside the room here and room temperature is 70 Fahrenheit, outside is 100 Fahrenheit. So so the heat will flow inside from outside. And then how would you find out the amount of heat being transferred through conduction? When you see conduction, you have to use this formula: temperature difference and the thickness of wall. This is thickness of wall, and the temperature difference is 100 minus 70, and K is the thermal conductivity, which is joules per meter per Kelvin, or we will talk more about it. But this is how this is for conduction, and for this is the heat, the formula for heat through the conduct. And for convection, the formula is overall heat coefficient, heat transfer coefficient times area times delta T. And if you talk about radiation, then you have to use another formula. Q radiation is um, Boltzmann constant, and delta T raised to power 4. I believe there is emissivity. We will talk about the black body radiation, which is emissivity is completely equal to 1. So we will talk more about. So my objective today is to explain the energy portion. This is my main objective. How would you find out the energy and the power of a device? Sometimes the device could be a nozzle, sometimes it could be a pump, sometimes it could be a, for example, another example I give you, a turbine, and if there is a dam, and you have a channel, maybe here, this is, maybe you can have a turbine, or you inside the channel, and you the water will rush outside. So if I ask you, okay guys, can, if the, suppose the height of this dam is suppose 100 meters, which is usually, height is usually represented by letter Z. This is our datum line. So you can find out, if I ask you what is the total amount of energy, um, so you will explain me, professor, this has a potential energy plus the kinetic energy. This is small e. Small e means specific energy. And you know the formula of potential energy is Gz, and kinetic energy is half V square. And sometimes we are, uh, this is in joules per kilogram. And sometimes we need the units in kilojoules per kilogram. In that case, you will have the Gz plus half V square whole divided by 1,000. I have to see somebody's trying to join this. Oh, this is not the one. Um, maybe this is a wrong team. So I added you guys in our team. Do you see? So maybe I can reshare with you the managed team. There are 55 students in the team. Please type in yes if you are added into the teams correctly, or you're having some issues. Okay, so I'm glad that you don't have any issues. Technical problems are resolved. Okay, now let's start. If you have any question about the technical problem, you will ask your professor. I will try to help you guys. Okay, let us begin our slide by slide explanation, which I'm trying to explain you in a big picture. Let's go into the details of our slides. So this is our big picture. Now let's go to the details of the slides here. So it is explaining you that a fan running in a well-sealed and well-insulated room will raise the temperature of air in the room. Why? Because the energy is being transferred from electrical to mechanical, and that is causing heat generating. That's why we will see the increase in the temperature because of the heat produced when converting the energy. Another case is refrigerator operating with the door open in the sealed and well insulated room. So it will generate heat. Okay, this is explanation now the different forms of energy. So as you can see, we have a different form of energy. Total energy is the sum of all the forms. Macroscopic, for example, kinetic energy, potential energy, and we are less concerned about the chemical energy or exothermic reaction, endothermic. Like we're not concerned with the microscopic. We're concerned with the macroscopic form, which is um, having some kinetic energy, potential energy. And if we go to the microscopic form, this is internal energy due to the molecules. Okay, so let's see this next slide. These are the formulae of different kinds of energy. For example, you guys have studied about the kinetic energy, half mv square, but specific kinetic energy is v square over 2. And kilojoules mean you will have to divide by 1000. So this is in kilojoules. Okay, potential energy mgz. Z, as I mentioned, is equal to the head of a particular um, body which is at a certain height from the datum line, and small pe means divided by mass. And the mass flow rate comes from the formula of density. As you see, density equals to mass per unit volume or mass flow rate per unit volume flow rate. And if we do the mass flow rate equals to the density times the volume flow rate is nothing but area times the velocity. Area is meter square, velocity is meter per second. So the formula has a unit meter cube per second for the volume flow rate. So this is the same thing which have been explained here, that rho AV. AV is the volume flow rate, area cross section times the average velocity. This is the average velocity of the stream, and the cross section area is pi d square over 4. You can find if this is water, then the density of water is 1000. So you can find out if I give you the area cross section. For example, this pipe has the area cross section as 1 meter square. So you can easily tell, and the velocity of water is suppose is 10 meters per second. You can easily tell the professor, this is the mass flow rate, rho a v. Rho is 1000, area is 1, velocity is 10. So it is 10 to the 4 kilograms per second. So this is how you find out the mass flow rate of a stream when you are given with the cross section area of that tube or the pipeline, and the velocity, average velocity. This is very easy. So I'm just repeating it again because you might need this information when you are solving the problems. You might need it time and again. So okay, the total energy including the internal energy. U stands for internal energy, and K is half mv square, P is the mgz. This is the total energy without dividing it by the mass. And small e is U plus Ke plus PE, and that's it. Okay, total energy per unit mass. And now we talk about a little bit more about different types of internal energy. Okay, now this slide is telling you that sensible heat or sensible energy, the portion of internal energy of a system associated with the kinetic energy of the molecules in which the temperature changes, and latent energy associated with the phase of a system. Phase is like liquid phase. When the phase is converting from liquid to vapor, then it just senses the heat to break the intermolecular forces rather than the kinetic energy does not increase of the molecules, but just the molecular bonding, like intermolecular forces, they are released. And that's why internal energy is represented by that time when you are releasing the forces, van der Waals forces between the molecules. So we are not going into the detail of the microscopic van der Waals forces, but you should know at least just one example I want to show you. Like if you take ice, suppose ice is in the container, this is all ice, and if you start heating the ice, if you start heating the ice, then temperature will start from 0 celsius, for example this is 0 celsius, and then you will keep on supplying heat, and initially the ice will start melting. This is the when you see the ice is melting, the temperature will remain constant, and temperature will remain constant up until the whole ice changes to a liquid. So ice goes to a liquid form, water. Once the this is suppose after a certain time, that this becomes water at 0 celsius, water at 0 celsius. This is at 0 celsius. Now the molecular forces, intermolecular forces have been broken down, and therefore the phase has been changed. This is the phase has been changed. When the phase is changed, now you keep on supplying heat, q is being supplied inside the container, then the temperature will rise. Temperature will rise until the whole liquid is at 100 celsius. This is the boiling point of water. Now the water, after it achieves the temperature 100 celsius, then what will happen? Then the phase will change again. It will, you keep on supplying. This is sensible heat. So this is sensible heat. This is sensible. This is, I'm sorry, I'm doing it opposite. This is not sensible. This is latent. Sensible heat is the heat when the temperature changes. This is latent heat. When the phase changes, there is a latent heat. The temperature remains constant. And once the temperature remains like after the whole water becomes vapor, all the water molecules have been changed to vapor, and vapors are at 100 celsius. Now you keep on supplying the heat. Vapor, the temperature, it will rise. Suppose this is vapor at 200 celsius. So this is sensible heat. Q sensible. Q sensible. This is latent heat. Q sub L. Q sub L. These are the things which you will learn more in detail when we will see the slides. Okay, let's go to the next line. If you have understood this concept of latent heat and sensible heat, please type in yes in your chat box. Okay, that's good. Sanjana says yes. Sarah says yes. Reena says yes. Okay, that's good. Let's go to the next slide. Okay, so you see, guys, this is the example of microscopic kinetic. If you put the turbine wheel over here, since it is not a channelized form of molecules, therefore it will not rotate. But you see, it is rotating when you channelize the flow through a certain tube or pipe, and then the buckets will have a fast speed of stream, and they will turn the wheel, and that will be a useful amount of energy. We will generate power for electricity. This is hydel power. So the thing is that the static form and energy is channelized, so it is better to channelize the energy to get the maximum amount of uh, work done from that energy. So the next thing is the nuclear energy. This kind of energy, when you break the uranium or fission reaction or fusion reaction, or uranium or plutonium, those are the types of isotopes, and you generate energy plus neutrons. The neutrons again are one neutron, it bombards the it combines with the uranium, and that creates further isotopes of selenium, rubidium, and generation of energy. And this happens very, very fast and creates a lot of energy and causes a lot of power generation for our um, whole city, or the submarine or a city aircraft carriers, etc., or even nuclear bombs. And the fusion reaction, when the two hydrogen isotopes are combined, and then creates helium, and a lot of energy is created, which is believe the theory is that in the solar system and the sun we are having fusion reactions. Okay, the next slide is about the mechanical energy. This is much more important as compared to nuclear, or this is also important, but now we will talk more about the mechanical energy. Since we are mechanical engineers, we will look more in terms of uh, energies. And then you will see, as I mentioned, this is a pressure energy. Pressure energy is per unit mass is pressure energy, I will say P per unit density. This is a fluid energy of the fluid per unit mass. So for example, Newton per meter square is the unit of pressure, and unit of density is kilogram per unit per meter cubed. And Newton, what is Newton equals to? Newton is also in consistency, it is equal to kilogram meter per second square. As you know, force is equal to mass times acceleration. And then we will use the same system. Okay, I'm going to replace this Newton by this system. So can I write down like this: kilogram meter per second square divided by meter cube, sorry, meter square, and then multiply by meter cube divided by kilogram. So then we are left with kilogram is cancelled by this kilogram, and this I'm sorry, I'm sorry, I want to show you that you don't need to do all this thing. This is explained to 1 meter. So what is this Newton meter? Newton meter equals to joule per kilogram. So this is the unit of energy per unit mass. And similarly, if you have v square over 2, meter square over second square, and if you multiply by kilogram, divide by kilogram, and then what is this equals to? Can you tell me? Can I write down meter square like kilogram, meter, meter? This meter square is twice written here, so can it divide by kilogram? And now what is this thing equals to? As I mentioned here, this is equal to 1 Newton, so can I write down like Newton meter per kilogram, which is again, units are consistent. I'm sorry, this is joules per kilogram. This is joules per kilogram for kinetic energy. Now we're talking about the potential energy. So let's see how the units are uh, d- consistent. So the gravity has a unit of meter, meter per second square, and the unit of height is meter. So meter square, I'm sorry, this is meter square meter square per second square. It's the same thing. You will do the same math here. So the unit of specific energy or energy per unit mass is joules per kilogram, joules per kilogram. And if you want to write down in kilojoules per kilogram, so you will divide by 1000. For example, if you have, if I say half v square divided by 1000, then the unit will be kilojoules per kilogram. And if you want to find out the difference at two locations, okay, I already explained this. You will multiply by mass flow rate to find out the uh, power. And if you have to find out the difference between the energies at two locations, so you can use the difference formula here. So this is the difference formula and multiply by the mass flow rate. This is how you will find out the difference formula. For example, if I explain you further about the energy difference. So what I'm going to show you here, for example, you have a diffuser. This is not a nozzle, but this is just like a diffuser which reduces the speed of the stream and increases the pressure. At location one, at location one, this is the datum line. Okay, this is a datum line. You see, this is Z1. Okay, Z1 at location one, Z1 is there, velocity V1 is there, and pressure P1 is there. And as location two, this is Z2, and the height is same, the center line. So the difference of the potential energy would be zero if you are doing the difference in the potential energy. But for the velocity, it has a different velocity, usually smaller, because diffuser reduces the velocity of a stream, and pressure increases. Pressure is higher. So pressure energy delta pressure, I would say pressure energy would be equal to P2 minus P1 over rho, and delta kinetic energy would be equal to half V2 square minus V1 square. This is how you will find out that each term, you will write down each term like G Z2 minus Z1, each term here. So, and then you multiply by the mass flow rate to convert into power. The unit of power is kilowatts, for kilowatts. Okay, guys, now we have done this theory. So let's go to the next slide. And before I go to the next slide, I would like to solve one problem for you so that you should understand some of the concept of the energy system. Okay, let's do problem number 17 of our book. So can you guys see the screen clearly? I want you to be in a technical difficulty. Okay, let us solve this problem. It's a very good problem to understand the concept of the energy differences. Okay, let's start. Consider a river flowing towards a lake. This is our lake, and this is our river. Okay, river is flowing, and it's like a height. You see the height difference here. This is the datum line. So Z1 is how much height. This is location in 90 meter above the lake surface, and lake surface is assumed to be the datum line, and Z1 is 90, and the velocity, average velocity of this. So if you know the small v is like 3 meters per second, average velocity is given, and the rate, volume flow rate, is given. And determine the total energy of the river water per unit mass and the power generation of the entire river at that location. So at this location, oh, I would say location number one, what is the total energy? Total energy. As you can see that if you go back to the formula, so this is the formula for total energy at one location. But here, don't worry about the pressure, it is not given. But let's see, if I want to write down the total energy per unit mass, is total energy, the unit of total energy per unit mass. So, and the power. So we have to find out two things, energy, kilojoules per kilogram, this is required, and the power at location one. What is the power in kilowatts? Two things are required, power generation, potential at that location. So let's do one by one. So I'm going to write down specific energy, or the energy per unit mass, due to the potential energy plus kinetic energy. I would say small e, so that you should not get confused that small letters are usually per unit mass. So we can write down Gz plus half V square. V1, I can say this is V1, which is at location 1. So then you will see what is G. G is 9.8. Z1, it is 90. Half V1, it is 3 square. Okay, guys, if you do the math, do you get 887? If you get 887 joules per kilogram, then this is what I have. Please, can you confirm in your open your calculators and help your professor whether you get the same number? And if you see E1 is this one equal to this one, 887. That's good. Brianna is correct. Okay, a little bit difference is okay. She's getting 87.4, but 887. Okay, now we have to find out in kilojoules. In order to get the answer in kilojoules per kilogram, you will divide this by 1,000 because you are converting it into kilojoules per kilogram. And that will give you the answer 0.887. This is your answer for the first question. If you have understood the first answer, please type in yes, and then I will move to the next part of the same question. Brianna says yes, and any other student, Molly says yes. That's correct. Okay, let's go to the next part. The next part is saying that you have to find out the potential of the power generation when the river is flowing at that speed. Okay, we know that E1 dot equals to mass flow rate times E1. And I mentioned that mass flow rate, it is equal to density times the volume flow rate. And density of water is 1,000 and volume flow rate is given, which is 500. So let's see, 500 is a volume flow rate. And now I'm going to write down the answer is 5 into 10 to the 5 kilograms per second. Now, in order to find out the power at location 1, or the power generation potential, 5 into 10 to the 5 times 0.887 kilowatts. Can you open your calculators? What do you guys get this number? Let me see in my small calculator. What do I get? I get 5 5 times 0.887. I get this number 44343500. That's what I have. And the one student is Brianna is confirmed. That's good. So this is in kilowatts. Okay, the same thing can be written as, usually this is a very large value. Can I write down like this? 444 megawatts, because 1 megawatt equals to 1000 kilowatts. And that's what I did. Divide by 1000 to find out the answer in mega. Usually for the large city population, we have the power generation at the powerhouse in megawatts. So this is how you will find out the answer. This is a very good example to understand the concept of this slide. If you understood this problem, please type in yes. Then I will move to the next problem. And if you still have some uh, issues, I will explain this. Okay, let's go to the next problem. Calculate the kinetic energy, total kinetic energy in BTU, British thermal unit. And there are certain conversion which I'll explain you in a bit. You have to find out the answer. The pound mass, the mass is given. Mass of the object is 15 pound mass, and the velocity is 100 feet per second. And you know the kinetic energy, half mv square. So I can write down half m v squared. And this is in terms of like pound mass and feet square per second square. And if you do the math here, so I'm gonna write down here 7.5 times 100 square. This is the this is in terms of pound mass, and there's a formula for 1 BTU per pound mass equals to 25037 feet square per second square. So you will divide it by 25,000. So if you divide this by 25037 feet square second square times BTU per pound mass. So you're left with this one, cancel this one, cancel this one, cancel this one. You're left with BTU only. So dividing this by 25,000, dividing this by 25,037 gives you 2.99 BTUs. So this is how you are going to find out the energy in terms of British thermal unit. There are certain more conversion which we will come across later today. Okay, let's do another problem here. Another problem is 2-10. Just a quick question. Do you want me to include this chapter in the quiz or just chapter 1 in the quiz and this one into the test? What do you suggest? I want to see. Taylor says no, please. Sanjana says just chapter. Okay, okay. The test. Okay, chapter 1 quiz will have only homework 1 and 2. No chapter 2. But remember, the following week you have to prepare chapter 1 and chapter 2. Okay, guys? So I'm not going to change the homework problem set for quiz 1, but for the test 1, you are required to prepare both chapters so that we will complete this syllabus in a timely manner. Okay, let's go to the. I see some students are still typing. Okay, let's see. I'm gonna show you how to solve this problem. Calculate the potential energy in kilojoules of an object. Potential energy is equal to mass times g times z, and the mass is given. The mass is 20, g is 9.5 at that location, z is 20. Now here this is below the datum line. So if you have a datum line and the object is located below the datum line, like in C, negative. So you will write on the negative. You are losing when you have a negative sign. When the object is below the datum line, then you are losing the potential energy. When the object is above the datum line, you are increasing the potential energy. And then this energy divided by 1,000 to convert it into kilojoules. Uh, So you get negative 3.8 kilojoules. Okay, guys, this is the complete potential energy. I'm giving you just a small questions in the beginning to understand the big concept. If you understood the small questions, then you should be able to solve large questions afterwards. So I'm going slowly rather than completing the chapter and rushing away. So I just want you to understand the concept first, and then we will move forward to the next. Let's solve one more problem regarding the mechanical energy, electrical energies. In this case, electrical power. Electric power is to be generated by installing a hydraulic turbine. So for example, a hydraulic turbine generator, it looks like this one. Okay, this is like a, I would say, I would say this is like a hydraulic turbine concept. Okay, don't worry about the question here. Just focus on this kind of thing here. So it is being generated by installing hydraulic turbine generator at a site 160 meter below the free surface. So here this is below the free surface 160 160 meter below the free surface of a large water reservoir that can supply water at a rate of 3500. So the mass flow rate in this question is given 3500 kilogram per second. Find out the power generation potential. We know that the power equals to the mass flow rate times the specific energy or energy per unit mass. Energy per unit mass due to the potential is Gz. And here this is the 160 meter above the ground. So 9.8 times 160. Okay, guys, now this is in joules per kilogram. Joules per kilogram. Since we do not have mass, if we do not have mass in our formula, this is per kilogram. But if we have mass in the formula, like over here, if we have mass, then it is not per kilogram, but it is just joules only, or kilojoules, depending upon dividing by thousands or no. So now you see, if you do the math here, you get a certain value. So I'm going to write down mass flow rate is given. So I'm going to write down the formula for power. In our book, the power is written by E dot. E dot is the power. not like P, but E dot. So M dot times E. So can I write down 3500 times E 9.8 times 160 divided by 1000. Please open your calculators and help your professor. What do you guys get for this answer? I'm looking at the chat to see if you can find the answer quickly. 5488. That's good. 5488 kilowatts. That's what I have. Or you can also tell me, your professor, this is about 5.48 megawatts. It is the potential hydel power, uh, hydel power generation. This is a potential. Let's do one more problem. At a certain location, wind is blowing, okay, steadily at 10 meters per second. Determine the mechanical energy of air per unit mass and the power generation potential of the wind turbine. So you see, wind turbines, they are implanted here, and you have a power generation. So the wind turbine and the airstream has a velocity, and the wind is blowing this velocity of 10 meters per second, and this is rotating, okay, and generating power. And then you, what is the power potential, power generation potential, due to this wind speed? So you know that formula is m dot times e, and you will tell me, professor, look, this is the kinetic energy to the speed. When you have, when you see the speed of a stream, you have to find out the kinetic energy per unit mass. Half v square, it means it is in joules per kilogram. If you see half v square by divide by 1000, this will be in kilojoules per kilogram. So make sure you follow this conversion, otherwise you will not have a consistency in the units and difficulty to solve the correct answer. So v square, can I write down 10 to the square divided by 1000? If you do the math for this one, you will get 0.05 kilojoules per kilogram. And then the next thing is, look, how do you find out the mass flow rate of the stream? We have been given the diameter of the, like the blades of this, the blade. So the diameter is the projection area. The diameter is this much. The diameter is given 60 meters, quite big. Yes, quite big diameter. And the air density is given 1.25 kilogram per meter cubed. And you know that density equals to mass flow rate per unit volume flow rate. And then you also know that the velocity has been given to us. So velocity, volume flow rate is equal to velocity times the area, and velocity of this air, it is given like 10, area it is pi by 4, d squared, d is 60. So you can find out the volume flow rate like this, and the density is given. You have been you are able to find out the mass flow rate from this formula. Density times the volume flow rate will give you the mass flow rate, and then 9 times pi by 4 times 60 square, and this is in kilograms per second. And then you will multiply by this one, and you find out the power generation potential, that is equal to 1767. Do you agree with your professor? Please open your calculators to see if you if you see the same answer. If not, I'm not sure what's, I will resolve this question for you. This is the formula. This is in kilowatts, okay? I see one student is trying to explain whether it's correct or incorrect. Just to verify this answer. M dot is 35,343 by one student, 35,343 kilogram per second. And if you find this, you can multiply by 0.05 to see if you get 1.761. I would say 1.77 megawatts. Do you agree with your professor? Okay, that's good. Brianna is correct. Okay, let's go to the next question. Uh, this you can solve it by. Let's do one more problem here. So let's do one problem. Mechanical engineering. We have to find, I'm focusing on the mechanical energy part since we are mechanical engineers and we have to understand how the energies are calculated for a device. It could be a, a wind turbine, a, a hydel power, or a nozzle. You should be able. This energy chapter is focusing on developing the problem solving skill for different devices. And now let's focus on this question. In this question, the question is asked two sites. Okay, for example, city A and another city is B. Okay, city A has the wind power generation potential. You have to find out E dot of city A or location A, E dot of location B, and compare which one has more potential to install the big turbines. Where would you install the big turbines to generate the power? It depends upon the speed of the wind and the location. First site A has the speed of the wind. It is, I would say, 7 meters per second, and it remains throughout 3000 hours. This speed remains that much. So the time duration, I would say, time is 3000 hours per year. The speed of the wind is steady, about 7 meters. For the other location, let us see the speed of, this is 10 meters per second, and it remains 10 meters for 2000 hours. 2000 hours per year. Okay, now you have to apply the knowledge. How do you, which site is best for installing the turbines? What I would say, look, what did we do? We used this formula. Yes, we use this formula to find out the energies per unit mass. So let's do this. Half V square and divided by 7. Divide by 1000. Why am I dividing by 1000? Because I will get the answer in kilojoules per kilo. I will do the same process for the other site location. Divide by 1000 to get the answer in kilojoules per kilogram. And 10 square divide by 1000. Okay, guys, and the answer will be in kilojoules per kilogram. And now the next thing is you have to find out the potential of the power. You remember the previous question? Look, this is the formula. This is the formula for finding the power generation potential. So I have to multiply by the formula. Now the question states that assuming the wind velocity is negative, determine the which power is the mass flow rate is proportional to the wind speed. So let me show you. When it says proportional wind speed, the diameter is kind of same diameter. You will install the same diameter. Let's assume the area of the wind is 1 meter, of the wind turbine is 1 meter, the projected area. So now mass flow rate, it equals to mass rho a v. That is the formula. Okay, now if the area is assumed to be 1, because the size will not change for this blade, assuming this is 1, the density of air, it is 1.25. Okay, area is 1. So the mass flow rate at location A will depend totally on the speed of that location, and mass flow rate of location B will totally depend upon the speed of that location. So let's use this proportionality in order to find out the mass flow rate, and then apply it into our formula to find out the power generation potential. So I'm going to use this equation. So mass flow rate is 1.25 times 7. Here, 1.25 times 10. Now we have found the potential. This is in kilograms per second. This is equal to 12.5 kilograms per second. Okay, guys. Now we have found the mass flow rate. Now this is at location A. This is mass flow rate at location B. Now let's do the math. So I'm gonna write down here, it is 1.25 times 7 times this one. I need your help to calculate this answer. What is E dot A? Please open your calculators and help your professor to find out that power potential. In the meantime, I bring it down here. Okay, guys, now I need your help for that one, as well as for this one. I need your help for this one too. It is 12.5 times EB. So what do you see? Sarah is trying to help me, and let us see. In my notes, I see 0.214 kilowatts for site A, and for the other one, I'm getting 0.625 for kilowatts for site B. That's what Sarah is doing. That's good job. Okay, now we have done this, and one student has confirmed. Look, now where are we going to use these hours? Again, we have still not completed the question, because hours are important. How many hours the wind speed will remain like this? So we have to do the math here. You know, kilowatts hour. Kilowatt hour is the per year, is the actual power potential. So I'm going to write down big A multiplied by E dot A times the time duration per year. So 0.214 times how many hours per year? 3,000 hours per year. Now you will help your professor. How many kilowatts hour per year do you get? The answer. E dot, this is for A. This is for B side. Delta time for B. 0.625 times how many hours is the speed is 2,000 hours. 2,000 hours per year. So in my notes, the answer for this one is 643 kilowatts hours per year. And for this one, the answer is 1250 kilowatts hour. I'm sorry, this should be not per hour, but kilowatts hour per year. So can you type in in the chat box which site would you install the wind turbine, A or B? If you compare the two answers, which side are you going to install the wind turbines? B. One student says B. Brianna says B. Any other student? I want to see some answers from other students too. Sarah says B. Some more students. Taylor says B. Sanjana says B. That's good. If it means you have understood the problem. So this is the design problem. How would you install the wind turbine if you're working in a research and design department of the department of energy? So have you understood this problem? If you have understood, please type in yes. If not, then try to ask me. I will try to explain you the answer. Okay, that's good. Okay. One more question. Let us solve one more problem here. Yeah, this one. This problem is just about conceptual question about the units conversion. So let me show you what I mean by that. A model aircraft IC engines produces 10 watts of power. How much power? How much power? The same power. I would say in the unit pound force per second. How much power in horsepower? This is just a unit question. So how do you be consistent in the units? So let me show you how do you go from watts to uh, foot pound per second. So let me show you 1 BTU, 1 BTU per second, 1 BTU per second, 1055 watts. Okay, and and 1 BTU per second is also equal to 778 foot-pound force divided by second. These are the two units you need to convert from watts to this much, and also for B part, this is for A part. For B part, you need this conversion like 1 horsepower. How many watts? So these are the conversion which you need to go from one unit to another. So let's do the first part, 10 watts. So part A. So the power is 10 watts. How do you go from 10 watts to foot pound per second? So let's go from here. So I'm going to show you 10 watts and use this conversion. Divide by 1055 watts times BTU per second. I will just write down per second in the denominator for your help. And then after you do this, or let me do this the other way, BTU per second. And once you do this, you are left with BTU per second only. And you know that 1 BTU per second equals to 778. So divided by 1 BTU per second is equal to 778 pound force times foot per second. Okay, guys, this is cancelled, this is cancelled, this is cancelled, cancelled. You are left with the last unit. This is what we need. So can you do the math to help your professor? Multiply 10. Okay, so if I were in multiply 10 and 778 divide by 1055, I get 7.37. Do you guys get the same number? This is the answer in foot pound per second. Let's see if someone confirms the same answer, or if not, then I will try to help you guys. Brianna says, yep. Okay, that's good. The next question is, how do you convert kilowatts or watts to horsepower? We know that 10 horsepower, 10, sorry, 10 watts divided by 1 horsepower equals to 746 watts. 746 watts equals to 1 horsepower. So if you do the math, you should get the answer 0.0134 horsepower. And you can confirm it later on. But now we have done a lot of questions. Now the next question, we still have 15 minutes. Do you want to have early release or a mini break to complete the whole time? One student says early release. I need 2, 3 more students for early release, then I will. Okay, guys. I'll see you guys next week. Thank you. Kelvin